Okay, so it's my great pleasure to start this series today with Eric Schulz. If you're from London, there's a good chance that you know Eric because he did his master's in cognitive and decision sciences at UCL, followed by a PhD at UCL, for which he got the Cognitive Science Society's Glushko Dissertation Award. He then hung around at Harvard for a little bit before leading a group at the MPI in Tübingen, and now directs an institute for human-centered AI at Helmholtz in Munich. And Eric has basically been at the forefront of using the tools of psychology to try and understand what it is that large language models are doing. And conversely, also looking at large language models as a way of modeling cognition. So I couldn't think of anybody better to start this series and given what we have in mind. So without further ado, Eric, over to you.
Yeah, thank you very much for the invitation and for organizing this meeting. It's just having looked at the speakers the other day, it looks like a really, really cool lineup, and I'm quite humbled to be part of this. So I will present today like a topic that we coined machine psychology. So you've probably by now all heard of these models called large language models. I mean, they are just everywhere at the moment. They were initially actually just designed to predict the next word or the next token, given a set of tokens that you provide to this model in context. For example, a robot may not, and then the language model tries to figure out what the next word in this sentence could be. However, once these models got scaled up and to ever bigger sizes of data and network sizes and compute and so on, other so-called emergent abilities showed up. These models can now, for example, write poetry. They might pass the medical licensing exam in the US or even the bar to become a lawyer. They are then consequentially already used in many applications, for example, code generators. I don't know about your labs, but people in my lab use LLMs very frequently when they are coding in Python, and one might even think that some students cannot do without anymore. They have been used as tutors, and Deutsche Bank is also using them in the financial services industry. So they are kind of permeating into any application imaginable. Yet we don't really understand how they behave. I mean, these abilities are called emerging abilities, not only because they emerge during the training, but also because, we don't really get when and how these models show them. So this has led some people to label them as unpredictable. Some left unsettled when, for example, Bing's chatbot asked the New York Times reporter repeatedly to divorce his wife and declared its love to him. And in general, we can definitely agree that there might be some risk in not understanding what these large language models do. So then how can we actually understand these large language models a bit better? So I would say that on the one side, there's kind of the standard approach. It's maybe the approach often used in computer science, where people focus mostly on performance. So they create a benchmark and they train their models, and then they try to see whatever model gets the best score in this benchmark. This has several problems. So, for example, just performing well in a particular task doesn't maybe even tell us so much about why the model does the thing it does, but it also suffers from things like data leakage. So, this is just like a student having seen the answers to your questions already. If these models are trained on tasks on which they are actually then tested, they might get them trivially right just because they've seen it before. This is actually sometimes one of the reasons why they do pass these bar exams and so on. So this leaves us to the question, could there be an alternative approach, an approach that is perhaps more focused on insights of behavioral mechanisms and so on? And I would argue that, psychology is an approach that, for centuries has tried to build models that are kind of custom tailored to understand another black box system, which is the human mind in terms of computational terms. So their tasks are really engineered for insights. The goal is to understand why an agent, here for example a human, does the thing they do. And data leakage is not as easily possible if these tasks are generated randomly from scratch every time a subject does them. Uh, so in the very first, I'm kind of walking you through like chronologically the things that we did and where we kind of are at the moment. So at the beginning, GPT-3 was kind of like the first model that we really thought can do some pretty amazing stuff. So then, together with my postdoc, Marcel Binz, we had this idea, can we actually administer psychological tasks to these models? So this here is a very canonical exploration exploitation task by Bob Wilson and colleagues called the Horizon task. It's a two-arm bandit task where you observe some rewards, you want to maximize your rewards, and then you can choose which arm of the bandit, which option you want to choose. And there's two conditions. One is the long horizon condition and one is the short horizon condition. Why are these two conditions here? Well, in the short horizon condition, it might actually make sense to sample this arm about which you know a little bit less than this arm, because you might gain some information. This exploration might give you some information that you can use later on to reap the rewards of this knowledge that you're getting. And this is basically just what I said. To the best of our knowledge, we were definitely among the first, if not the first lab in the world that then took these tasks and actually submitted them to a large language model. Back then, that was only GPT-3. So here we describe to the language model what is the actual task, like it goes to a casino, needs to play with these different machines, and it needs to optimize rewards, like maximize rewards. Then we give it its past choices and the rewards these choices delivered as history in the prompt. And then we just ask it, which machine, given this knowledge, which machine do you want to choose right now? Then it chooses a machine, we generate the reward, for example, from a normal distribution, and add that to the, append that to this history, and submit the new prompt to the model and ask it again. And this actually can then be used to generate data sets that look pretty much like the data sets that we analyze from humans, and then we can run models of exploration, exploitation on the data that these large language models generated. And the first thing is we can just look at, how often does the model actually choose the best arm, like the better of the two arms. We see actually that GPT-3 was already as good as the human subjects in this task. So I'm showing this here because for computer scientists, they would now declare success and they would say, look, GPT-3 is human level performance, let's all go home. But if you actually analyze, with computational modeling, how much does this model engage in either exploitation or exploration? This is by regressing uncertainties onto whether it chooses left or the right option. We see actually that whereas humans really tend to explore quite a bit, GPT-3 essentially mostly just exploited, so it wasn't really exploring like a human at all. And back then, in this PNAS paper, we showed that actually, even though this model is not bad in decision making and kind of like model-based reasoning, in this exploration type tasks, it was very unhuman-like, and in causal reasoning, it really, really sucked. Yeah, this is basically, I'm jumping ahead. So we did this over a bunch of domains, and we saw that, sometimes it showed good performance and was human-like. Other times it showed good performance, but that performance was not very human-like at all. And, in some cases, causal reasoning, it was just not good at all. But, this was kind of the early days, kind of the wild, wild west of doing these tasks with large language models. To 2022, we started this. Back then, you could do it on one model. These days, that is definitely not enough anymore. So we did a bunch of follow-up works that I just wanted to mention here, where we showed that you can improve these models when you just submit the same task repeatedly. We can actually do some stuff with like belief updating and so on, and we can induce anxiety-like states. But I'm showing this here because this actually all accumulated then to a thing where Julian, in a heroic effort, instead of doing like one task with one model, actually did 7 different tasks that measured different components such as the prior weighting, likelihood weighting, directed exploration, random exploration, metacognition, and so on. He took these canonical tasks from the psychological literature and submitted these tasks actually to, I think it was more than 40 large language models. And basically, this now means that you can really profile these large language models. So you can try to find a computational phenotype of how these models behave across different scenarios and compare them to humans. So one thing here we can actually do is take the same base model like a llama model or across the same classes of models and then see how do different things affect these models. So now we can actually make a more precise science of how things change these models in their behavior. And Julian did this here. And for example, one thing he found in our PNAS paper, we actually, funny enough, we already said this model is not good at exploration and causal learning. Maybe it should learn interactively from humans, and that would improve these things. And just shortly after that, machine learning people actually introduced this reinforcement learning from human feedback, which is a method of kind of like post-training adapting these models to human preferences. And this we actually found increases things like metacognition. So metacognition here means how well the model knew about how much it didn't know in different tasks. And funny enough, actually, metacognition, it was as good as the human subjects in our tasks. Or these models were as good as human subjects. In risk taking, a funny thing, just that's why I wanted to show it here, is that open source models oftentimes actually took less risks than proprietary models. And I thought that was interesting because people, especially in companies like OpenAI, sometimes argue that the development of these models should be left to companies because they know how to make them safe. Whereas we actually find that these oftentimes these open source models can actually be less risk-taking than these proprietary models. Okay, so this was kind of where I thought, okay, now, I mean, I kind of walk you through what we did as a lab. Uh, Now we thought, okay, we did this first paper with like some canonical tasks with one model. We did a bunch of other things, and then we really did this big cognitive benchmark where we did it across many tasks and many models. And then behaviorally, at least from my side, I had the feeling we did a lot already. And then more and more people were doing this stuff also. And then that's usually a good signal for me to, like a foraging signal to like go on and try to forage the next patch. Uh, and we actually then thought about the following. Well, with these llama models that were actually released by Meta, we could actually not only do kind of behavioral sciences on these models, but we could actually try to start doing kind of neuroscience on them. So analyzing what they do, not only based on the behavior, but also on the neurosignatures that we find, so their weights, because we now have access to the weights. So a student of mine, Chan Demijan, actually did this, and he did this across three different tasks. One is just kind of this two-step task. The agent goes to an orange and then to the next step and gets differently sized rewards. A navigation task in a grid, and also a community structure task. I will mostly just focus on this, but everything that we did on this thing also works for the other two tasks. And the method that we used is a sparse autoencoder, which basically just projects the weights of the model upwards into a larger space, tries to associate what's here with the behavior, and then projects this down again and tries to have these two sides here to be as similar as possible. And I know this is kind of like a big plot, so let me walk you through just some of this stuff. What they find is that in terms of rewards in these tasks in general, only really the big model like the Llama 70 billion, with 70 billion parameters, really got traction and performing quite well. So we then used this model actually. And what Chan showed was actually that this model was quite nicely explained by a Q-learning model, better than by other models. And then what we could actually do is we could identify neurons like weights that are actually responsible, that we think were responsible for the reward prediction error in this model, like while it was doing this task in context, and then lesion out these weights. So by just setting them to zero. And by just setting them to zero and comparing them to other control lesions, we actually find that we can knock out how the model learns from prediction error. So it does get, it is going to get predict less well by these temporal difference learning models. And it really shows that you can then not trace anymore any signal of the prediction error in the internal weights of this model. And this is just the first step because here we kind of just lesion the model, like, setting something to 0, and then we show that this targeted thing really doesn't work anymore in the model is the first step. Now, one other thing that Tancred is trying to do is to see, can we identify A, other algorithms in this model? And B, could we actually increase the propensity of these models to engage in these algorithms by increasing the weights instead of setting them to 0? But that's still work in progress. We also then tried to see, okay, we've done a lot of these things already with the language, but if you talk to people like Josh Tannenbaum, for example, he would tell you that these kind of like nice little cute bandit tasks are not really the tasks he's interested in. What he's really interested in is stuff that he calls common sense. And we actually read this. I mean, I've always been a fan of this nice paper that Josh and Sam, Brandon Lake, and Tom Ullman wrote called Building Machines That Learn and Think Like People, where they lay out different tasks that they think intelligent agents should be able to solve if we would declare them as being able to learn and think like people. And these 3 tasks back then were intuitive physics, causal reasoning, and intuitive psychology. So then what we just did was we thought, can we do these tasks with vision language models? So models that can not only get text prompts, but also images as inputs. And we took the most canonical tasks from Josh and, like his kind of wider web of collaborators and submitted them to different vision language models in context and queried them. So this, for example, would be like submitting a picture of tower blocks and asking these models, how stable do you think this tower block actually is? Or we submitted these kind of figures where an agent tries to avoid a certain patch and then ask them, how much does this agent actually like going over that patch? And so on. And we used 5 different vision language models that were available at the time. There weren't so many VLMs that really got any traction at all, but these 5 we could get to work. Okay, so I show you here the intuitive physics task. So this is, by the way, led by Luca Schulze-Buschoff and Edith Akata. And they first did these guys, they did a check where they just asked the models, what's the background color of the image that you see? It's just like establishing that these models really, do they know anything about the picture they see? And we see that all of the models that we tested kind of get that right. But then already in intuitive physics, if you ask, okay, what's actually the block color from top to bottom? A lot of these non-proprietary models actually fall out. This is a general thing, by the way, that you see is that oftentimes the proprietary models are stronger than the non-proprietary models until the point when the non-proprietary models finally catch up. So here only GPT-4 and Claude 3 got this right. But then if we check for stability judgments, these 2 agents actually do get this right above chance. A funny side note is here that, like people always say that humans are so great at common sense, but actually when you analyze some of this data, you also find that they're not always so great, but they're still like seem to be better than the VLMs. And then what Luca and Edith did was they basically tried to see, okay, how well does actually how well do these models in their intuition match to the intuition of people? We did usually in Josh's lab, what they did is they calculate aggregated scores and they correlate them with each other. We did not do this because I think this inflates the correlation coefficient quite a bit. Instead, what we did was we did a mixed effects regression and we calculated the pseudo R-squared based on a Bayesian regression model. And then you can see that actually GPT-4 is not too bad. This has some correlation at least with the human judgments, but of course, human to human is more highly correlated. But also, you see that here actually, this is something that I also didn't know before. There is substantial disagreement between people about the stability of the very same building blocks. Okay, this was one thing where we thought, okay, it somewhat works, maybe partial success. But actually in intuitive psychology, so judging about costs and rewards of these agents as they go to different goals, we see again video only GPT-4 and Claude, maybe even just GPT-4, pass these like initial checks. But when it comes to relating them to human-like intuitions or even the ground truth Bayesian agents, none of these models get it right. So actually in social inference is something that we find very often that in intuitive psychology and theory of mind type tasks, these models are just not very good. And this is a shame because we interact with them quite a bit, right? We would want them to be not too bad at this. Uh, so actually, we tried this then out to develop this a bit further because we thought, okay, so far it's always been one agent doing one task, but Edith had this cool idea of letting actually two agents play with each other. And we can do this with the same approach as before, where we basically give the rules of a game as prompt, we give the past history of choices and interactions as well, and then we ask these agents to make a choice. They each make a choice, they get a payout, and then we adapt their individual histories. And basically, we found that there are these two action games. So this year is one that's called the Battle of the Sexes. It's unfortunately a very like anachronistic name, uh, where a couple has to decide whether they want to go to football or ballet. One person, let's say the woman, likes football more, and the other person, let's say the man, likes ballet more. Uh, so they would really prefer to go to their preferred option, but if they end up at different places, there's no fun in not doing things together. This is a general form of a coordination problem. And Edith did this with all possible two agent, two action games that exist, because you can do it with these models and with a lot of different models. I will just show you like two kind of results that we thought were interesting. So one is that when we let these agents play the famous prisoner dilemma, so where you can either decide to cooperate or defect, right? And you let them do this repeatedly, like over 10 rounds, then the best agent that we found, GPT-4, seems to apply a strategy that is sometimes called the grim trigger. So this means that this agent, if you only ever so defect once, keeps defecting throughout. It's like very unforgiving in that sense. And that's not very human-like here because humans usually tend to play a form of either tit for tat or even forgiving tit for tat, where like they mirror what the other person does, but even they are a bit forgiving. So if you defect even once, I could maybe still think, okay, let's try again. Maybe you had a bad day or whatever. Let's try again to cooperate. Um, in this Battle of the Sexes game, a common strategy that emerges in people is to alternate. And given that most of the audience here is from the UK, this is probably something you've all witnessed when you go to the pub, right? Where someone gets the first round and then, the other person gets the second round and so on until everyone is drunk. Uh, and we let actually GPT-4 here play against an agent that we just hard coded that does alternate. And we see that GPT-4 really just doesn't get the alternation at all. Just always goes for the option, no matter which one it is, that it prefers the most. Uh, and Edith then developed this idea that we took from kind of autism research, which is we framed social chain of thought. So here the idea is that you actually ask the agent, what do you think the other agent will do, just in general, without making it social? What do you think they will do? And then given what they will do, what do you think is the best thing for you to do? And this kind of like takes it a bit out of this social inference thing and makes it a bit less, or it's a bit more abstract. And we actually see that then GPT-4 does start to alternate, and we see this actually consistently. And in fact, because Vivios asked us to try this with humans, so we did. Uh, so we basically let humans play with LLM agents, so GPT-4, and either the base agent, so unlike with just the normal rules and so on, or the social chain of thought prompted agent, and randomly they either played Battle of the Sexes or Prisoner's Dilemma first. And what we see is that in general, when we do this social chain of thought prompting, then the scores of both agents go up, and the people also think more likely that this agent is actually a human, and successful coordination also increases. This is actually a form of maybe getting these agents to be a bit better in the social inferences that they have to do on a daily basis by using theories of psychology and social reasoning. Okay, So so far I've kind of shown you like where we were until maybe end of last year, beginning of this year, where we started out discussing, understanding these behaviors of these agents behaviorally. We first did it with one model, then we did it in one or like a few tasks. Then we did it with many models and many tasks, did some neuroscience and some social interactions and vision. But across all of these tasks, we kind of kept finding that these models are not always very human-like, or there are cases where they might diverge from human behavior. And this led us actually to this idea, like, is there a way to actually turn these models into models, at least predictive models of human behavior? And together with Marcel, we actually started this not so long ago, where we took a base model back then, I think it was Llama 2. We fine-tuned this model on psychology experiments to then create another model that we call Centaur. So it's like, supposed to be a mixture of a llama and a human, but we couldn't find a good animal for that. So we settled on what Marcel calls the nearest neighbor. Uh, and then once we fine-tuned it on actually human data of psychology experiments, we can test, can this model actually now predict holdout experiments or holdout subjects better than other models? So this is what it looks like. We basically give to the large language models the history of a subject, and then we ask it to make a prediction for that particular subject, what that subject will choose. And then we can actually see, okay, how well does it predict, given the history you give into this model, the subject's choices on the next trial, and so on. And back then, what Marcel and I found was that, in these two data sets, one was collected by Tom Griffiths et al., where they have these like many, many choices, as like gambles always between different options. We could actually get this model to predict human choices better than the best model back then that was kind of available in the psychology literature. Beast, which is this model that repeatedly wins this competition that Edo hosts, I think, every year or like every now and then. But also in these exploration-exploitation tasks, like the Horizon task, it also performed better for holdout subjects than the best known model, which was this hybrid model, a mixture of random exploration and directed exploration. I forgot something here. So actually in this paper, we also tested, can this model make predictions for completely new tasks? So we fine-tune it on these two tasks, and then we see, can it make predictions for a holdout task that was not these two tasks? And we used the task that was conducted by Stefano Palmenteri's lab. It's kind of a mixture of these two things, and we did find that indeed the model can make good predictions for this left-out task. And this then really made us wonder, like, okay, what are the limits of this? Like, oops, could we actually just take all tasks that we can find, like any cognitive tasks that we can find human data on, like, scrap the whole interweb, uh, make these into these like make this into this text format, and then fine tune a model on all of these human tasks, like human data from all of these tasks. So this is what we kind of did in the last maybe 1.5 years, where we now have a data set that Marcel coined Psych 101, which is roughly 200 experiments in total, more than 15 million human choices. It's quite large and it contains a lot of different tasks. This is just like if you try to sort this a bit, there's like, there's a lot of bandits because that's what we do a lot in our lab. There's like, category learning, function learning, Markov MDP processes like the two-step task, decision-making, gambles, memory, probabilistic reasoning, all sorts of different things. And then what we try to see is, okay, can this model actually make predictions for the first thing is, can this model actually make predictions for new subjects in the same task? So this would be like similar tasks, but new subjects. And we tried this. So this was a lot of effort for all of these tasks here. We coded up the best model that we could find that is a domain-specific model. And then we tested this domain-specific model in its prediction for new subjects with this model that we call Centaur, so the fine-tuned model, but also the unfine-tuned base model. And the pattern is essentially the same everywhere. So you can always make better predictions by using Centaur than you can make by using just Llama, and much better than the best domain-specific model for each of these tasks. But not only that, we can actually use this model to not only make predictions for like next choices, we can also actually use this model to simulate completely new subjects from scratch. So it's like completely generatively simulate just what would this model do in this task. And then fit models and see can we recover human-like patterns, for example, of model-based and model-free behavior or exploration, but also like I think this is kind of a reasoning task. And this actually now opens up possibilities of actually having a model to which you could submit almost any psychology task that can be expressed in natural language and get data that is at least to, to many degrees very human-like. And we also tried here different other variants of like further generalization. So far this was same task, different subjects, but we can also use, new subjects and a new cover story for a task that we fine-tuned on. So in the two-step task, for example, there's a version of, going to different planets, but people also have collected data on a carpet version where you have to decide where to travel with a magical carpet. And again, we see, that Centaur makes the best predictions for these new cover stories. It also makes the best predictions for uh, basically completely modified problem structures. So here we never had the three-armed bandit, but we had two-armed bandits in this task. But Tobias Hauser and his lab, they collected actually subjects on three-armed bandits. So we used Centaur here to make predictions for this three-armed bandit task. And again, we found that this model works best. And last but not least, Marcel also tried this a completely new domain. This is a Dunning-Kruger effect type task that Tom Griffiths did, where there isn't even a cognitive model. It's very out of sample, but still Centaur makes very good predictions of human subjects. I should say that this is always pseudo R squared. So the actual absolute values of these cannot be easily interpreted, right? Because it's based on the log likelihood compared to the log likelihood of random guessing, and random guessing is different depending on how many options you have and so on. Okay. We also tried other things. For example, we checked, okay, can this model actually make predictions about, the brain? Like, does it get more aligned to brain data? So we used the task by Tukute with F. Fedorenko, where they let people read sentences. This is again quite out of sample, I would say. So where basically, people need to read the sentences and then they regress this to like the fMI data. So we would find activity in the language network. And basically what we find was that this is across layers of these models that, our models make better predictions than the Tukute model, and that the fine-tuned model is better than the non-fine-tuned model. So Centaur is better than no fine-tuning. So I think this is quite cool because this is kind of, we think, one of the first attempts at the foundation model of cognitive science. So a model that can really make predictions for all sorts of tasks that you can like phrase as text and give to this model. But to me, this is just the beginning, and many things are possible. I think we can use this for discovery, for example, query this model about tasks that, this model is quite uncertain about, and then go out and actually test these models so we can do kind of automated discovery and so on. But I also would like to scale this actually up further. So the next step clearly is, integrating vision. So not all tasks can be phrased as vision tasks. And we have seen in the common sense tasks that there are interesting tasks that are beyond language. So we would actually expand this soon to also incorporate visual input. I would also very much like entering individual differences. So we can actually do this by just giving information into the prompt. So, this was done by an X-year-old. And then see if we can actually reproduce. I think the first step really would be developmental psychology, reproduce developmental effects at a large scale. This is next step. But we can also, try to do this with psychiatric disease and, go into developmental psychology and computation psychiatry and so on. And so ideally, I would want to have a model that you can give any task, both language and vision. You can give some more information about the subject, and it generates you data that is indistinguishable from that subject. Um, and another thing that I'm currently looking for a PhD student for is to expand this to like the generation of brain data. So right now, this model always just generates the next token, so it's like behavioral choices, but nothing holds us back per se to also generate brain data that goes with that choice. Whether or not that would be fMRI data or more physiological data is still to be discussed in our lab. There are pros and cons, but this is something that I would also like to push. Okay. Ah, yeah. And then, we posted this on Twitter. I also presented this at the Gatsby. And then, of course, right now, this is all purely predictive. I'm sure this will come up. Uh, so then some people said, this is not what a cognitive scientist does. We are not only interested in prediction, we are also interested in model building. So I was like, okay, maybe we can actually create an LLM to which you can just submit your data, and that LLM will actually generate code of different models. So basically, you give the data of a subject, and this model returns to you and guess of the model that it thinks describes the subject best. So because then you cannot say anymore, oh, this is just prediction, because now we're actually doing model discovery um, um, with this kind of approach. And my postdoc, Milena, she started this. So she basically started with a simple case, a decision-making case, where the model just needs to decide between take the best and telling. The take the best is just focusing on the features in order of importance and then deciding for the option that is best on the first or second feature. And telling is adding up all of the features and then taking the option that is best on all of these features. So here, for example, take the best if you just focus on the first one would take B, but telling you would actually add them up and then choose the one that has the highest sum. And first thing is already cool if you just give it like generated data and then always with the right code. The model already can generate the right code for new data at 100% accuracy, even if you add noise. So it can really distinguish quite nicely between these two different strategies. So maybe that's not so impressive for some people because it has seen a bunch of realizations of that code. So we always give it like, this is the human subject data, and then we say this data was generated by this model. And this is like the training data. And it has training data of take the best and telling, and then we give it new data that we generated, and we ask it to write the code. And there at 100% of the time writes the correct code. But Milena is also currently trying to see, okay, can it actually generate a completely new model? And so this is now trained on two models, and it needs to actually produce the code correctly for a third model that is a model from the literature. And for take the best and just decodes it some, but it's actually telling it can do that. So it has just seen these two cases, but it can actually generate completely new code. Uh, Here it still suffers a little bit, but I have some clues why this might be the case because sometimes these models actually make similar or related predictions. So sometimes actually not even clear, is the true model the best model in terms of describing that particular realization of that model, right? Because noise can matter there. And but because we have seen now, and she's also has done this now, it's not in the slides, with a banded task where she kind of trains it on two or three models, and it can actually make really good guesses for the code of a fourth model or third model. My aim is to now scale this up Centaur style, where then in the end we would have a foundation model where you can give in the description of your task and the human data, and our model would help you to give you a very good guess from which you can start building your model. So it would say, given this task and this data, this is, I think, a good model for this task at hand. Okay, so in conclusion, I think it's really impressive of how far LLMs have come. This is Descartes finally understanding the principles of intelligence, and for that he turned himself into a robot. Yet it is not clear how they do the things they do, right? We don't always know where these emergent abilities come from. I think that psychology can contribute to our understanding of LLMs by providing models, computational models that have been designed to understand certain types of behavior and abilities. And we have then in the end actually mixed now our interests in like classic cognitive science and model building and cognitive and large language models in trying to build cognitive foundation models at scale. And with that, I would like to thank you. Thank you, Ulrike, for the invitation. I would like to thank my lab, of course, for doing all of this work, and also the people who actually paid for all of the things that I presented. Thank you very much.
Thanks a million, Eric. That was amazing. I'm going to turn off the recording now, and then we have about 15 minutes for questions.